So today's goal for section 5.1, polynomial functions, is I can sketch the graph of a polynomial function utilizing understanding for end behavior and turning points. So here we have a flat version of a box. Has anyone ever made a box out of paper where you cut out the corners and then you can fold it up and make it into a box? So that's what this is before it becomes this box right here. And it represents the cardboard box that the city of Hamilton uses to create the boxes for their world famous bottled tap water. So if you go to Alexander's Market, you can buy a whole box, and it's literally a cardboard box with bottled water of Hamilton tap water. So write an expression for the length and width of the box. So keeping in mind that it tells us right here the length of this right here is x. So the length right here is also x. And the entire length of the box is 12. So if we're going to find out the length when we fold it all together, the length would be 12 minus 2x. 12 minus 2x. And then the width, similarly, looking here, would be 8 minus x here and x here. So 8 minus 2x. Next question says to find the surface area of the box. Since it's laid flat, that makes it pretty easy for us. We can just find the area, which is length times width. And using the expressions that we wrote in part A, 12 minus 2x and 8 minus 2x, we would distribute because it says right in standard form. We know that that means there's no parentheses. 12 times 8 is 96. And 12 times negative 2x is a minus 24x. Come here, negative 2x times 8 is minus 16x. And the minus 2 times the minus 2, x times x, so that's going to be a plus 4x squared. Standard form also requires that it's in descending order according to the exponents. So notice we have an x squared. That should be first. So we're going to put the 4x squared first. Combine our like terms. The minus 24x and minus 16x is a minus 40x. And then plus 96. So now we have a variable expression that represents the surface area, or the area of our box. Lastly, it says find the volume. We already know area is length times width. We add one more dimension when we're talking about volume, so we have length times width times height. So the height of our box, if you think about folding that up, would just be the value x. So we're going to multiply our previous answer. So the 12 minus 2x and the 8 minus 2x, we're going to multiply those all times x. We don't have to redistribute. We've already done that once. So we're going to just substitute that in. And distribute our x. So 4x cubed minus 40x squared plus 96x. And now we have a variable expression for the volume. So this is a practical application of polynomials. We connected this with our local business. So if you are having an event, you can actually order Hamilton bottled water through the city, or you can go pick it up at Alexander's Market, and you'll see further applications of this same problem further on in our unit as we think about maximizing the volume. So how can we use this same piece of cardboard and fold it together in such a way that it creates the largest volume possible? We'll be able to answer questions like that. For now, though, this is our first lesson in Chapter 5. We're going to talk about a few vocab terms. Monomial. Monomial is a number of variable or variables multiplied together. So you have a whole number, it can be any number. A number, a variable or variables, with whole number exponents. That's key. Whole numbers, remember whole numbers would be starting with 0, going up by our counting numbers. They're positive, 1, 2, 3, 4. Those types of numbers. Not fractions and not negative numbers. So the exponents would have to be whole number exponents. And you can have a product of numbers and variables. So for example, we might have something like 9x cubed. That is a monomial. We could have 3xyz. We could have negative 2a squared. We could even have 12. Those are all monomials. The degree of a monomial is just the value of the exponent. So for example, we have 9x cubed has a degree of 3. Okay, so since the exponent value is 3, the degree is 3. If we have, let's go with the negative 2a squared, the degree is 2. If we did x, let's just say x, that would have a degree of 1. Our 12 up here, we'll just come up and label that, has a degree of 0. Because there's no variable. So the degree is 0 if there's no variable. Polynomial. A polynomial is a monomial or the sum of monomials. The sum of monomials. So it might look something like 2x squared plus 5x plus 1. That's a monomial. Or sorry, that's a polynomial. You can see that there are 3 terms separated by plus signs. Another example of a polynomial might be 4x cubed minus 7x. Degree of a polynomial, that's the greatest degree of its monomials. So for example, our first example up here, this would have a, I'm going to just point up to that guy, the degree is 2 because the x squared is the highest degree. So that's degree 2 here. This one right here would have a, what, degree 3. Lastly, standard form of a polynomial. It's arranged in descending order according to the exponents. or degree. We did that in C Part B. We did that in Part B above, right, where we wrote it simplified form, but then standard form required that we rearrange things. So descending order according to degree. The blank of a polynomial function affects the shape of its graph, the degree. So degree tells us a lot about the graph of a function. The degree of a polynomial affects the shape of its graph and determines the maximum number of turning points. We'll see that in a minute. A turning point is where a graph goes from moving upwards to moving downwards, or where it changes direction. It also affects the end behavior, or the directions of the graph to the far left and to the far right.